HyperSpy, the tool I've been using to analyze my multidimensional data sets and for everyday day-to-day use. And I think it has a couple of very nice ideas that many other packages may benefit from. And in general, it has very nice concepts that are useful when thinking about multidimensional data sets in general. So very quickly about me, I'm a PhD student in electron microscopy group in Cambridge. I'm mostly funded by the ERC. However, my college, Peterhouse, also contributed to this event over here, allowed me to come here. So what do we do in electron microscopy? Mostly we have a very thin specimen and we have our electron beam focused to a very fine probe, and essentially the whole physics don't really matter for us. The whole idea is that anything you measure is that from one red spot over there. And there are multiple things we can measure. Most often it's just a number, so you essentially get an image. Often you get an image actually in each point. The thing is that I can only draw 3 dimensions here on the screen, so we'll deal with spectra, which is actually pretty typical. We very typically measure spectra. So a spectrum is essentially just a one-dimensional array, right? So I'll draw that as a line of cubes in one dimension. And then as experiment goes on, you move the probe to a new position, you acquire a new spectrum, and then you go on until you map the full data set like that. So in the end, you're left with a 3-dimensional data cube in this particular example. It could be 4 or 5 dimensions, it doesn't really matter. In this case, it's just something that is easy to draw and imagine. However, the intuitive way to think about the same data set, exactly those same dimensions and numbers, is the way we measure it, as a rectangular array of spectra, right? Yet another way to look at this sort of data is like a stack of images. The best example of that would be any movie. All the frames would be in 2 dimensions, and then as you go along the time, you stack the images, right? So any movie is essentially a 3-dimensional cube. And when you think about it, in all these 3 cases, it's the same data, those 3 same dimensions. The only thing we do in our minds is that on the left side, we separate the x and y dimension as being something you just select your data over, and then the z dimension is the one that's important. Conversely, on the right side, you do the opposite. The x and y, the frame axes, are the important ones, and the z only selects the time you're interested in the movie or the slice in a 3-dimensional data cube. Actually, in the middle case, none of the dimensions are important since they only specify the location of that particular number that you are interested in this way that I've drawn the data over here. So that hopefully essentially captured the whole idea of HyperSpy. What we just did here was we drew the line in our minds separating some dimensions as being the important ones and the others as being less important, that you only iterate over, that you select certain parts. And that's the idea of HyperSpy, to separate the overall dimensions of the array into signal dimensions and into navigation dimensions or spaces. So just to iterate over, again with 3-dimensional example, because it's difficult to draw hypercubes, you could look at it as a volume, where all 3 dimensions in this are in the signal space. And it's actually reasonable to look at it only as a volume as a whole. Then you can move over one of the dimensions to the navigation space, and then suddenly have a stack of images. You can move over one more dimension, and then you have an array of spectra, right? Finally, you can move the last axis over to the navigation space with no more axes or dimensions left in the signal space. And then your signal is just a number. And these are all equivalent ways to look at the same data. And we embrace this whole idea in HyperSpy, and we inbuilt this separation of signal and navigation spaces. And as a result, there are interesting things we can do. So let's actually have a look what we can do. I'll first import the HyperSpy and NumPy and set up the plotting, and load some data that I prepared beforehand. And since the signal dimension essentially defines how you look at the data, so it's either images or spectra or just numbers, the core class in HyperSpy is a signal. In this case, it's a 2D signal. because the overall array that we started with was three-dimensional, and we just defined it to be that we're interested in 2 dimensions in the signal space. That's another point. HyperSpy signal is essentially just a wrapped NumPy or soon Dask array. It's not yet implemented, but I'm working on that. And one of the important things, obviously, in an array is its shape, because it defines the size and dimensions of the array. So HyperSpy has that separation, as you can see. There's the navigation shape on the left, and there's this signal shape on the right. And with this separation, we can actually do interesting things. For example, plotting this three-dimensional data set is now completely defined. You don't have to render it, because what you are interested in are frames that flip as you go along a spectrum. So you can do this just as easily. It could be 5, 6 dimensions. As long as the signal space is 2-dimensional, we can plot it. You just iterate over whatever's in the navigation space. All this information is stored in the axis manager, which essentially shows us that the axis, which axis is where, and that the axes also have names, physical units as an offset and scale, and all that. Now, it would be pretty useless, actually, if you couldn't swap one axis from one space to the other. So let's do just that. Let's define our signal so that the x and y are now in the signal space. So what I just did here essentially moved the stack axis to the navigation space and y back to signal. And if I plot again the same data set, suddenly it seems to make a lot more sense, right? Hopefully. As we go along, we may actually recognize some of the things. So that's actually an important thing. Even though you may measure data one way, it may not be reasonable to look at it in that same direction. You may want to tweak it around and turn it around. Obviously, you can do it the other way around. We can swap essentially what's the signal navigation space and have all the x and y axis in the navigation space and the other one, the stack axis, in the signal. And when you plot that, you do essentially the other way around. You have all the you navigate on an image, and the spectrum changes in the background. The screen's a bit small, so I can't actually very quickly not make them overlap, but essentially works quickly. It's done in matplotlib because it's been done for a while, and bokeh wasn't around at that time. OK, so since the signal is actually just a wrapped NumPy array, we still have broadcasting, indexing, and various operations. However, we separated the whole dimensions into 2 spaces. So all of these operations perform either on one space or the other. For example, indexing. You can index navigation space with the inav method and signal space with the isig method. And the column 3 would obviously, as you would hope, give first 3 elements in the navigation space. And it does. It works fine. Here's the navigation space for the new signal. It has only 3 elements, so that's worked as expected. However, here in signal space, we have from 0 to 1 in one axis and from 0 to 1 in the second axis, because there are 2 signal axes, right? And you would hope you would get just a single element because you select the one corner. However, if I run this, we get 18 and 15. And that's actually by design, because in HyperSpy, you can slice any of the axes either by indexes or indices if you pass integers, or you can slice by physical units if you pass floats. And you can mix and match. You can specify the start in indices, the end in floats, then the step in indices again, and it doesn't really matter. That's very useful when you actually have physical data that is important. So you want to select that and that particular micron, and it's very useful. We have usual operations like mean, variance, sum, and so on. And if it requires an axis, then you can pass the name of the axis as well. So that just works. We support NumPy universal functions. And actually, they write in the title of the result signal what they did. That's very useful, apparently. I just recently discovered that. And we also have broadcasting. But again, since the two spaces are separated, it works separately in navigation space and in signal space. So if I have a signal that's purely in signal space, this data set, for example, there are no dimensions before the bar. And then the other data set that I just calculated up there only has navigation space. There are no axes after the bar. If I multiply just the data, the actual NumPy arrays, they're not compatible. You wouldn't be able to multiply that. But since in HyperSpy we have the two spaces separated, you can do that and just broadcast as you would expect. OK, the next thing I want to show you is events and interactive regions of interest, and essentially interactive recomputation. The best thing to do is to actually show what it does and what happens, because it's pretty straightforward once you've seen it. Yeah, essentially, as you move the widget, it automatically recomputes whatever is the sliced signal. There are a number of widgets we have, the rectangular, just the one I like. And if I manage to click on it, because it's so small, you can resize it as well. It works fine. Actually, this figure that I have right here in the middle is just a signal that has its data updated as required. So we can do other stuff before plotting. For example, we can calculate a histogram, and that will be updated live as well. I'll just resize it again as I move it around, and so that's just updated. That's very useful as well when dealing with real physical data. You can also notice that the number of bins in the histogram is recomputed. It's not constant, so that's because we used some fancy histogramming tool from AstroML, I think. OK, the next thing is machine learning. We use a lot of machine learning, the simple one like PCA and independent component analysis when dealing with our data. And with the two spaces separated, it's actually trivial how to perform all these operations. Normally, they're just defined in a matrix. But you can do that with 6-, 7-dimensional data set as long as you have the separation, which dimensions are in the signal space and which are in navigation space. And I can perform the PCA with just one line, the first one. The second line actually plots the scree plot to figure out how many significant components there are. I will not plot the results because it will get messy on the screen. It's not that big. I can perform the independent component analysis with yet another line, and it all gets unfolded and folded back into the correct shape, irrespective of the actual dimensions of the data. The 3 dimensionals over here that I have is just because it's easier to understand looking at it the first time. And we can have a look at the results of the decomposition. So we have the whole stack separated almost nicely. Not exactly, because I added Poissonian noise, which is actually very difficult to deal with, usually. OK, let's close the stuff that we don't need. The next thing is mapping. Essentially, when you have 6-dimensional data set and you want to apply image rotation to that, it's not straightforward how to do that. However, again, if you define that out of your 6 dimensions, only 2 actually really matter, so you have the 2 frames, and the rest are just something you iterate over, it suddenly becomes trivial. You just apply to the function in the signal space, you iterate over navigation space. So we can do exactly this. We have the same data set, which is 3-dimensional. We import from the SK image the rotate function and just apply map and rotate all images by 30 degrees. I hope you trust me that it's not just the first one, but all of them are actually rotated there in background. It's more interesting or more useful when you want to rotate by different amounts. So what you do is you just wrap the array that contains your angles that you want to, in this case, angles. It could be any function as you get. You just wrap the function in a HyperSpy signal and make sure that the navigation spaces for the argument and for the signal that you apply to are identical. So I create this angles signal, which has the same navigation space as we had before. Inside the data is just an array of numbers. And if I, again, apply the same, it's exactly the same command, irrespective of the actual size in here of the image that we're interested in. And if I plot it again, you will see that they're all rotated by different amounts, so it just rolls around the full stack. OK, and then the last thing I wanted to show you here live is model fitting. Well, almost show you. We essentially have one-dimensional and two-dimensional models. By that, I mean not one-dimensional, two-dimensional data sets, but signal space has to be in 1 or 2 dimensions. I'll just quickly create it. And our models are, I would say, completely general. We build up the model function that you fit to the data as a sum of components. So obviously, at first, you start with no components, but then you can add either from our pre-built library, for example, a Gaussian, that we now have in the model, or you can write your own. We support SciPy. You just pass a string that defines the math, essentially. Nothing more fancy, as long as the x is the signal axis. So we just pass it. It gets compiled a function, and derivatives are calculated, and you have sine function as well. And then you can set the starting parameters. I'll just quickly to go to a pixel that has some data, so that it's more interesting. OK. I'm not sure if it's visible. The data right now is shown with red dots instead of the line, so that it's easier to distinguish between the model, which will be drawn in blue. And then essentially, you can just use notebook widgets to set the values that you're interested in. Increase that. So we'll just move around the Gaussian a little bit. We add some sine interactively again. I mean, it's usually very useful when you have more complicated functions, and it's not trivial how to give it the starting parameters. So once that's done, you just call fit, and in this case, it doesn't fit because it's a rubbish example of functions, but it doesn't really matter in this case. I don't want to fit it right now, right? That only fits it for that one particular pixel. If I wanted to fit it for the full data set, again, doesn't matter how many dimensions in the navigation space, I would call the multi-fit, and that would be it. That actually brings me, whoops, the other direction, to a problem that's very common in all optimizations, all essential optimizations, which is the local minima problem. What happens is when an optimizer is given a cost function represented here by the black curve, it's given then a cost function and a starting guess as the red ball. And what the optimizer does is usually just goes downwards, down the hill, right, until it finds the lowest point, and that's your solution. And as you can see, that it doesn't really work that well all the time, because even with equally good solution, you can get stuck in what's called the local minimum and never reach the actual solution that you were looking for. And as you might expect, that actually gets way more difficult when you add additional dimensions in the navigation space. So let's see how a typical optimizer actually approaches this. So you select the first pixel, you have your cost function, you have your pretty good starting guess, and that's great. You fit it, you find the actual solution that you were looking for. You go to the next pixel. The cost function shifted a little bit. It's still very similar, but it's not identical. Otherwise, it wouldn't be interesting to fit the whole data set, right? Your final solution in general was a lot better than your first guess. So you just copy over the parameters. And then you fit it, and then you go to the next pixel, shift it slightly a little bit. Again, copy over, fit it, and then go to the next row, and you're in trouble. This pixel is actually, in this case, exactly identical to the very first one we solved. However, due to the problem how the actual optimizer approaches multidimensional data sets, it will not work. And there are essentially two problems with that, how the optimizers approached it. The first one is that it only ever used the last point of information. It ignored the first 2 pixels, right? It only used the very last one in that line. That's obviously not a smart thing to do. You should use as much information as possible if it's useful to you, of course. The other thing is how it went along the data set. That's essentially because it was just the easiest way to code. It almost never is the actual reasonable way to go fitting the data set, to just go row by row. You probably want to follow some path that actual data set suggests. So what I did is I built an algorithm called SciPy, which in this video shows how it uncovers, how it fits the navigation space of the signal of the whole data set, and it follows. It doesn't actually follow raster scanning order as I mentioned. But it follows the path of least resistance, essentially suggested by the data. And it uses all local available information, or not necessarily local, but all available information that's reasonable to use to estimate it, the starting parameters for each pixel. So essentially, mostly gets around the starting problem, the local value problem. OK, so summary. The signal and navigation space separation is actually very important, and it's very, very useful that I hope more packages will embrace this idea. And it allows you to unambiguously and intuitively do plotting, various operations, mapping over n-dimensional data sets, and helps a lot with machine learning, at least the parts that, the simple parts that we've used. We also have interactive recomputation and regions of interest. We have models that are completely general for one-dimensional, two-dimensional signal spaces. And when they get really difficult and when you have large data sets, we have SciPy. Or no, we do actually have SciPy. It was released yesterday or this morning, I don't know. And with that, I wanted to thank you. And here's my own personal and the HyperSpy information, and I'm open to questions. Yes?
Can you make the actual optimizer pluggable? Because also like with SciPy, you get things like differential evolution, and you get simulated annealing, which are also fairly good at sort of dealing with local.
Yes. The question was if the optimizer can be pluggable. Yes. SciPy is essentially the layer between the user and the optimizer. It doesn't do optimization at all. It just deals with the starting value problem. Okay. So I actually myself use 3 or 4 optimizers and just see whichever feels best. Yes?
So modern systems are quite capable of operating out of core. Do you have any persistent storage model that you work with? Or do you run off of disk or flash? Or is it everything in core? It looks like everything is in core.
So far, everything is in core. I have a pull request open for a laser signal, which essentially replaces the NumPy arrays with Dask arrays. So that will be coming shortly, hopefully before the end of the summer, when I have to teach people use it. Yes. Anything else? Well, thank you.
I actually had a question.
Oh, OK, sure.
So I use a lot of multidimensional data, but they're all in different arrays. Would this be as simple as concatenating them first and then like setting the navigation versus the signals?
I suppose it depends on the actual shape of the arrays. If they do not match, then it's not that trivial.
Yes.
Yeah, I think the X-ray is better for the actual wrangling the whole thing into a single object, the package X-ray. I believe it does that well. I think it's worth actually looking how to combine the two ideas. Since I think the HyperSpy's the biggest asset is the idea of navigation and signal spaces, because it allows to perform a lot of operations over n-dimensional data sets, and it just becomes intuitive to think about. OK, thank you very much.